Well, welcome to the SETI Talks. And again, we want to thank our sponsor, Leonard Tramiel, who's here in the audience. Thank you, Leonard. I'm Edna DeVore. I'm the Director of Education at the SETI Institute, and I have the pleasure of introducing my boss. Bill Diamond is a technology executive with long experience here in Silicon Valley. He's got more than 20 years of experience in photonics and the optical communications industry, and a decade in X-ray and semiconductor processing technologies. His corporate background spans the spectrum from venture-backed startups to Fortune 100 internationals, with responsibilities ranging from engineering and operations to sales, marketing, product management, and CEO positions. And today, Bill is the president and CEO of the SETI Institute. His first nonprofit venture, at least as Bill likes to joke, the first organization that's nonprofit on purpose.
True story.
True story.
True story.
Before joining the Institute, he was VP of Product Management and VP of Sales at I'm not going to do this right. Oclaro Incorporated, an optical communications company. And before that, he was CEO of Wave Splitter Technologies, raising more than $75 million in investment capital for the company's development of optical waveguides in one of the world's first 8-inch silicon PLC wafer fabs. He's got his fingers and his background deeply enmeshed in what this valley does. He was also a CEO at Dense Light Semiconductor in Singapore and X-Radia Incorporated, that's now part of Zeiss in Germany. And he led the team that developed the world's highest resolution X-ray microscopes, as well as manufacturing the only commercially available zone plate lenses for focusing X-ray beams. So quite a strong technological background. Earlier in his career, he got to romp around Europe for 6 years as the optoelectronics business unit for AT&T Microelectronics, later Lucent, and then returned to the U.S., where he was the part of the executive team for a successful IPO of eTech Dynamics and its subsequent sale for $15 billion. He's been the president of Comet Technologies, a U.S. subsidiary of Comet AG in Switzerland. And I wonder if that's where you acquired your lovely Swiss wife.
Could be.
Could be. And so I'd like to welcome Bill. His background educationally is a BA in physics from Holy Cross College and a master's in business administration from Georgetown. And he's the president and CEO of the SETI Institute. Thank you.
Thank you. Thanks very much, Edna. That was longer than it needed to be, but in what's definitely been an interesting career here in Silicon Valley, I couldn't be more happy or indeed more honored than to be at the helm of the SETI Institute. And for those of you familiar with our weekly colloquium series, you know that typically we take sort of a deep dive into a rather small pond of information on any of a variety of topics having to do with space science, astrobiology, aeronautics, astrophysics, etc. So today we're going to take a rather shallower dive into a vast ocean, which is essentially the science of the SETI Institute. Before we dive into the talk, however, let me just introduce a group of people who are here with us today. And you'll hear more about this in my talk, but every year, thanks to Edna, whose leadership in the Center for Education for SETI Institute is key here, we host a program called the REU program, Research Experience for Undergraduates. So we host about a dozen summer interns with backgrounds in physics and astronomy and biology and chemistry and various things, and they team up with scientists at the SETI Institute and spend a summer of 10 weeks doing hard work and good science. So I'd like to welcome the REU students and maybe ask if you would just stand and be recognized, but because we're so happy to have you here. Very good. Okay, so here we're going to talk about today the science of the SETI Institute and the search for life beyond Earth. So our journey begins by understanding where we come from. Where do we come from? So if you go back far enough in time, we can trace our roots and our origins to the sub-Saharan African continent. If you go back even further in time, hundreds of millions or billions of years, we can probably trace our origins back to the first creatures that grew feet from what had been fins and flippers and emerged from the oceans to walk on land. But that's not really where we come from. In fact, those chapters are rather recent chapters in the evolution of life, very recent chapters. Really, where we come from is here. It's the star stuff. We are all brothers and sisters of the cosmos from the early universe, and ultimately the inhomogeneous collection of material and coalescence of matter into the formation of galaxies and the birth of stars. And ultimately, however, I think we recognize that stars don't necessarily make a very hospitable place for us to reside. They're a little hot, a little warm, a little dangerous to set foot on. So we need planets, we need something solid to set foot on. So planets ultimately became formed as a byproduct of star formation in the early universe, and of course still today as stars continue to be born. So it's a process that takes millions and billions of years over time. It's a process which it requires the tug and forces of gravity to pull matter together to coalesce into rocky bodies or gas giants. And while it's a very long and extended process of physics, if you will, and cosmology, there's also stochastic events or random events that are associated with the formation of planets. It's not always just this peaceful, let's gather the matter together and form a planet. Sometimes there are stochastic events and impact events that actually have a relationship to the evolution and development of life on Earth. So it's a contact sport. Is there water around? We think, at least to understand life as we know it, water is an essential ingredient. Where does water reside? Well, we know that comets, for example, are icy snowballs that travel the cosmos. Some people believe that comets were responsible for delivering water on Earth. Others believe that water was a natural byproduct of the Earth's early formation. Nevertheless, one thing seems to be clear, that water is also abundant in the universe. In fact, this is an imagery taken from radio astronomy work from scientists at the Max Planck Institute using their 100-meter dish in Germany and also the Very Large Array in New Mexico, showing the presence of water in the very, very early universe, looking at very far distant galaxies. So water appears also to be abundant. So now we have kind of this primordial soup. We have a solid substance on which to form, to stand, and for gravity to take hold. We have liquid water, we have thermal energy, thanks to the tug of war of gravitational pulls between planetary bodies and stellar objects. We have minerals, we have the development of an atmosphere. Indeed, we have all the natural ingredients, all the raw ingredients. And then the question is, but is life as abundant and as frequent as all of these raw ingredients would suggest could be the case? So we've wondered about this. We've been wondering about this really from the beginning of time. We've wanted to know if we are a unique occurrence. Do there exist many worlds, or is there but a single world? This is one of the most noble and exalted questions in the study of nature. Now, interestingly, this is not a question that was asked by Carl Sagan or by Neil deGrasse Tyson or by Neil Armstrong or even by Seth Shostak. This question was asked in the 13th century by the German Catholic bishop Albertus Magnus. Albertus Magnus pondered this question several hundred years ago. He was a philosopher, an astronomer, an educator, a learned man, and one of only 36 doctors of the church that have been so named since the beginnings of the Catholic Church. So an interesting individual, and like Albert, we have all yearned to know the same thing, and that is basically, are we alone? So enter the SETI Institute to answer that question. The SETI Institute is a nonprofit research organization interested in the nature and existence of life beyond Earth. We've got about 70 PhD scientists here, and their research is world-class. We also do a lot of education and outreach. Our interests range from nearby planets to the distant stars.
Of all the places scientists look for extraterrestrial life, the one that's garnered the most attention is Mars.
There's water on Mars. and its surface is covered with channels that suggest that maybe once in the past there were rivers and lakes and even an ocean. Could there also have been life on Mars? Maybe. One thing for sure, we're looking.
We live on Earth, but Earth lives in space, and Earth gets constantly bombarded by these little rocks like this. These rocks give us clues about our origins, of the beginning of Earth, the beginning of life.
I'm Molly Bentley. Welcome to Big Picture Science, produced at the SETI Institute, where researchers investigate the nature and origin of life.
The SETI Institute's one-hour radio show, Big Picture Science, has more than 100,000 weekly listeners, telling the public about our research and, as part of the deal, getting more people interested in science.
It took the New Horizons spacecraft about 10 years to cross the solar system and get to Pluto, but nobody's been disappointed by what we found. We see huge plains of ice, we see mountains, we see glaciers, we see moons that are spinning backwards. It's just a gift that never stops giving.
One of our experiments here at the SETI Institute is to look for evidence of intelligent life. And to do that, we use a set of 42 antennas up in the Cascade Mountains, which is called the Allen Telescope Array. We point these antennas in the directions of nearby stars, hoping to eavesdrop on a radio signal that would tell us that somebody is out there.
There are few science questions as compelling as Earth's place in the universe. 10,000 generations of Homo sapiens have looked at the skies and wondered if there might be living things elsewhere. But ours is the first generation with the ability to address that question. The SETI Institute is leading the search for an answer.
In any case, this is a video clip about the SETI Institute. It's about a minute-and-a-half clip and talks about the science we do at the SETI Institute and the research we do and how we are unique as an institution and an organization in that the reason we exist is to answer that question of are we alone? So let's take a closer look. So who we are. SETI Institute is the only research organization in the world that's really combines all of the physical sciences, many of the of other sciences, including the computer sciences. We're branching into other new and interesting areas, including neural sciences. But what we do is we combine the efforts of the full spectrum of scientific endeavor to answer this single question, are we alone? And I think this is what, to me, makes the Institute so fascinating and separates it from so many other research organizations, where very often what you have is a singular problem with a singular science being applied to that problem. Here, we apply the entire spectrum of the sciences to answer this question because you need them all. They become, whether it's chemistry or physics or astrophysics or astronomy or biology or zoology or microbiology, they become the jigsaw puzzles that, when combined, form the picture of life in the universe. What do we do? So we're an international center of excellence in education and research and outreach, and we're focused on the exploration of planetary habitability, the signatures of life, and the evolution of intelligence. What is our mission? Our mission is to explore and understand and explain the origin and nature of life in the universe and to apply the knowledge gained to inspire and guide present and future generations. That's why we do what we do. And who benefits from this? Everybody benefits from this. We have a passion for exploration and discovery, for sharing knowledge as scientific ambassadors to the public, the press, and the government. That's an important part of what we do. So the research is the underpinning of the Institute in terms of executing the science that we do to answer this question. But if in the end of the day we're not sharing our work and contributing that body of knowledge to the public at large, we're missing a key part of our mission statement. So that's who benefits. So what we're trying to do essentially is we're trying to understand how did the universe evolve from its early beginnings, from the Big Bang, from cosmology, and the early expansion of the universe and the coalescence into galaxies and stars. How did we go from cosmology to chemistry? How do we go from chemistry to biology? And how did we ultimately make this journey from biology to philosophy? That's what we're trying to find out at the SETI Institute. So what is SETI? Any of you flown on Virgin America Airlines? So you've seen that part where they say in the safety video, for the 0.001% of you who've never used a seatbelt before, here's how it works. So for the 0.001% of you who have not don't know what SETI means, so it is the search for extraterrestrial intelligence. That's where the acronym derives from. And that has, for most of its history, involved the use of radio telescopes, including the Institute's own Allen Telescope Array up in Hat Creek, California. And these are deployed in the search for signals which would suggest the presence of an extraterrestrial intelligence, or indeed technology. New techniques are also being used that include optical techniques, where we're using sensitive optical systems attached to telescopes or wide-field cameras to detect the presence of laser pulses, which might also be indicative of some type of communication or indeed propulsion technology. So Frank Drake, who is one of the early founders of the SETI Institute, still has his office at the SETI Institute and comes in once a week or so. Frank is really one of the pioneers of SETI, and he wrote what is considered by some to be one of the most famous equations in science. Of course, there's E equals mc squared. Electrical engineers will say there's V equals IR, but this is right up there. It has a few more variables, but this is the Drake equation. And Frank put the Drake equation together at the beginning before participating in a conference that was being held at the National Radio Astronomy Observatory, at that time new observatory, in Green Bank, West Virginia, and this was in 1961. And he was really interested in this part of it, which is n. What's the number? Can I try to predict, or can I try to come up with a formula which would allow me to predict or speculate on how many intelligent or technological civilizations might be out in our own galaxy that might also help us indicate whether there's some point in actually looking for them. So his equation is what I call a reductionist model, in that it's a little bit like a funnel. Each variable to the left is further filtered by the next variable to the right, and ultimately it yields an answer, or can yield an answer. And you can find this on lots of websites where, for example, you can plug in your own variables and see what comes out. It's kind of fun to play with. But we start with the variable r, star, which is the rate of star creation in our galaxy. Next, we have the fraction of those stars that have planets, f sub p. And we'll talk more about that now. This is one variable that, thanks to the Kepler work and other work in looking at the discovery of exoplanets, this is a variable that's increasing its value over time as we learn more. Average number of planets per star in the habitable zone. So what fraction of the planets that are orbiting stars exist in that area that's the right distance from the star and the star's energy flux to maintain and sustain liquid water, the so-called habitable zone. What fraction of those that have the ability, based on their distance from the sun, from their sun and star, to support life, how many actually go on to develop life? F sub L, sorry. And then the fraction of those that ultimately develop intelligent life, F sub I. And what fraction of those might ultimately result in a civilization that can develop technology that would be capable of revealing itself through the transmission of signals into space, F sub C. And then there's my favorite variable of all, which is the letter L. That's the lifetime of civilizations capable of transmitting signals into space. So once you get to a point where you have technology, how long do technological civilizations last? If I remember correctly, I think Frank's number for this is 10,000. And the way I see things going today, I think he was an optimist, but that's for a different talk. In any case, that's the letter L. So that's the Drake equation, and while he was using it essentially to try to make this predictive model of, are there likely to be other civilizations out there that we might be able to detect, what he unwittingly did was essentially write the roadmap for astrobiology, or the roadmap for understanding this question, are we alone? In the early days of SETI work, the base of operations, if you will, was the Arecibo dish in Puerto Rico. So the search for life starts with this variable n sub e, that is habitable planets. That's where we can begin our search for are we alone, or are there others out there? It culminates with F sub c, which is this existence of civilizations where communicative technology may have evolved. So we can use instruments like radio telescopes to do studies of SETI where we listen for signals. And in the case of Arecibo, it remains until next year when the Chinese dish is done, the world's largest and most sensitive radio telescope. This is a picture of it sitting on top of that mountain in Arecibo, Puerto Rico. And many of you are probably familiar with this. You may have seen it in movies like James Bond or in Contact or other places. But it's quite a sight, and it is quite large. Just to give you a sense of scale, so you can see this receiving dome here suspended above, and you can see on the side a stairway, and right there on that stairway is a person. So it's huge. This is 300 meters across, so 3 football pitches wide. And that's where the first work was done. And it was clear then, as it is still clear now, if we could detect a narrowband radio frequency signal, and we could tell that this was coming from deep space and verify that it was coming from someplace other than Earth and something other than a satellite of our own making, this would be a pretty definitive indication of intelligent technical life beyond our solar system. We haven't had that wow moment yet. We've had some close calls, but we're still waiting for that kind of signal. So have we made contact? Not quite yet. Dr. Jill Tarter, who is also one of the founders of the SETI Institute, is on our board of trustees and is an early pioneer in this field. She likes to make this analogy that, why haven't they called? Well, we've only just begun to listen. And in terms of the scale and scope of the universe and the fact that this is not just a spatial problem, but it's also a temporal problem in terms of the overlapping of civilizations, especially if you remember that L variable, which may be 10,000 years or less. There's a spatial problem and a temporal problem. So we've really just begun to listen, and we've done the equivalent with the kind of detection work we've done since the beginning of that technology back in the 1960s. We've done the equivalent of dipping a measuring cup into the ocean. And if you took a measuring cup and dipped it in the ocean and you looked at it and you didn't see any fish, you didn't see any whales, you'd be mistaken to assume or to draw a conclusion from that there are not any. But that's where we are. We're still in the infant stages of this SETI endeavor. Some of you may have come across the SETI Institute in the movies. In fact, some people may be surprised to know there really is a SETI Institute because you've only seen it in the movies. It was featured in Independence Day. I think the opening sequence in Independence Day involves my fictional predecessor doing some putting in his office and learning of a signal coming in that seems to be a valid and real signal. Contact, made in 1997 and starring Jodie Foster. Jodie's character was really based largely around the work and the life of Jill Tarter, although her experiences in the movie ended up being a little bit different than Jill's, much to Jill's dismay, I think, if you ask her, but there's still time. And then Another Earth in 2011 pondered a situation in which 2 identical Earths come into contact with one another. And the directors of the SETI Institute, in fact, I think the character in the movie is a woman, probably based on Edna, they talk to each other. And there's 2 SETI Institutes in that movie because there's 2 Earths. But in fact, these are fictional representations of the real institute. So what do we do at the SETI Institute? We work to understand the miracle of life starting at its most basic level, from the formation of molecules and the development of prebiotics to the evolution of advanced organisms, sentient beings, and intelligence. So we want to know a few things. We want to know, how does this happen? We want to know, why does this happen? And also we'd like to know, where does this happen? Ultimately, the question is, has it only happened here? Most of us don't think so, otherwise we probably wouldn't do this. But this is the question we're trying to address. We have 3 core centers of activity at the Institute, and these are the Carl Sagan Center for Research, which is really where all of our scientists are embodied under the Carl Sagan Center, and that's where all of the work gets done, where we publish in peer-reviewed journals. We work with colleagues at NASA Ames, at other NASA sites, at JPL, other academic institutions and research institutions around the world. So that's the core science of the Institute under the Carl Sagan Center. We have the SETI Institute Center for Education. You met the director, Edna. This center is really focused on grant-based educational programs, and we'll learn a little bit more about those programs and some of what we do and the impact that these programs have, which is surprisingly significant. And then we have the Center for Outreach, which is really the vehicles that we use to communicate the work of the Institute and share it with all of you. and we'll explore each of these three core activities in a little bit more detail. The Carl Sagan Center for Research is headed by Dr. Natalie Cabral, who actually is also with us today in the audience. As Natalie points out, the Carl Sagan Center explores the evolution of habitability and life in our solar system and beyond through the multidisciplinary perspective of all the physical sciences. And again, as I said from the very beginning, this to me is the most wonderful and amazing part of the SETI Institute, this combination and this multidisciplinary approach to the singular question. We have a series of different research thrusts or research groups within the Institute, within the Carl Sagan Center, and these take us back to the Drake equation, which, as I mentioned, is really more than just a predictive model, but actually this roadmap for astrobiology. And the different research divisions that we have within the Institute can be applied to different variables in the Drake equation. So we unravel and examine the Drake equation in close detail through the different research areas we have. So what are they? The first is astronomy and astrophysics. The second is astrobiology. The third is climate and geoscience. The fourth is exoplanets. The fifth is planetary exploration. And the sixth is SETI work. So you can see, again, how these map on the Drake equation. And we have researchers who are parts of each of these, a total of 75-odd scientists, and some of them are wearing more than one hat, but in each case we also have a head or a chair of these departments, and they, together with Natalie and other advisors within the Institute, form the Science Council. And the Science Council has the charter of helping to guide the research we do, to direct it, to go after the relevant kinds of funding resources that are out there, and indeed, as we're beginning to do now, more than any time in our history, derive and develop SETI Institute's own missions and our own science programs and our own science priorities that we will fund and execute. So we have what we like to call cycles of exploration and discovery, which is really the interplay between these research areas. And again, one of the most interesting things about forming the Science Council, establishing these areas of research, has been the ability to generate collaboration amongst and between the scientists in those various groups. So each research division addresses key questions regarding the nature and origins of life, how it came to be, where we might find it, and how natural and stochastic events might lead to the evolution of intelligence. So what we'll do is look at each of these in a little bit more detail and the questions answered in each. So the first is our astronomy and astrophysics research area. That's really looking at going back to the far left of the Drake equation. How do galaxies, stars, planets, moons, minor bodies form and evolve? What is the path that leads from prebiotic organic compounds and ultimately to life? So here we have actually a proto-planetary disk being shown on the left side, and because it's difficult, in fact, to visually show some of the work that our astrophysicists do, a lot of it is using computer modeling and theoretical tools or data sets from space probes and satellites, but they're quite prolific in their publications and their participation in various conferences. These are examples of some of the recent papers that have been published by our scientists in the astronomy and astrophysics section. And by the way, one of the other things that you'll find on our website is we now share with everybody the proceedings, if you will, of the SETI Institute in terms of monthly reports. So you can go onto the website and you'll see there a March and an April and a May report, which is essentially all of the published papers, all of the invited talks, technology developments, technology reports, et cetera, of the Institute. So you can now go and peruse all the work that our researchers do and dig further into areas that might be of specific interest to you. Next we have the exoplanets. The exoplanets are really looking at how abundant and diverse are planetary systems. How many exoplanets have developed habitable environments, and how many are common, how common are Earth-like planets? There have been really 3 tools deployed for the detection and characterization of exoplanets. The first being the radial astronomy method, which used the relative wobbling of a star planet system, when you have a large, massive planet in close proximity to its star and it revolves around the star. The center of mass between them is not at the center of the star, so the star wobbles. This was the first method by which exoplanets were detected. The other tools that have been used are the GPI system, the so-called Gemini Planetary Imager, which is using a technology called adaptive optics, and they've bolted this system on the back of what is now here in this picture on the left side, the Gemini telescope down in Chile, and that has been able to actually image exoplanets for the first time. So to actually take a picture of a planet revolving around a star that is not the sun. Very, very dramatic. And then we have the Kepler Space Telescope, which has used the method of light curves, or basically looking at what happens to the brightness of a star when a planet or other body transits in front of that star. And the very, very slight, and it is very, very slight dimming that results in staring at that star and then looking for that periodic dimming by staring at the star for a long time reveals the presence of exoplanets. This has been, I think, one of the most exciting developments in astrobiology, if you will, or in this question about are we alone, is the fact that as far as planets are concerned, we're anything but alone. So GPI and Kepler, the Gemini Planetary Imager, again, what you're seeing here are two different images taken at two different times in December of 2014 and September of 2015, showing this planet called 51 Eri b. The star is about 100 light years from Earth. So this is a planet imaging a star 100 light years from here, and that's an actual image of it. And again, this is kind of a breathtaking wow moment for mankind to actually be able to image a planet other than revolving around a sun other than our own. The Kepler Space Telescope, the father of whom is sitting in the audience with us, Bill Barucki. Many of you know him from NASA Ames. This has been, again, one of the most spectacular missions and most profound, from my perspective, in NASA's history. As a result of the Kepler telescope, we have identified 4,700 planet candidates, 2,327 confirmed planets. The SETI Institute has researchers on the Kepler team. They are in charge of a lot of the data analysis and data collection and dissemination from the Kepler Space Telescope, and also our scientists are involved in the adaptive optics and the deployment of that technology on the GPI Planetary Imager, together with colleagues at Stanford and elsewhere. So this, from my point of view, has really transformed our understanding of life in the universe, or the potential for life in the universe. And again, it's draws us to this conclusion that planets are everywhere. So here's a chart that is actually already quite out of date. It's as far back as 2013, but it shows how many planets, candidate planets, as of January 2014, were identified by Kepler. You can see the size of the planet goes up on the y-axis. Earth-sized planets are down here. Neptune planets, about 4 times Earth size, are in the middle here, and large Jupiter-like planets are up here. And then orbital periods are along the x-axis, with an Earth year of 365 days being about here. So you can see a lot of the data is based on planets that are close into their star, and that's not necessarily because that's where they all exist, but it's certainly an artifact of the way that Kepler works, which is to stare at a given star for an extended period of time. So very, very long orbital periods are going to be naturally a little more difficult to detect. Nevertheless, a rather stunning discovery and revelation. This is actually looking at the star field of the original Kepler data set. These are the CCD images or imagers of the Kepler telescope, and what they show you here is this rather uniform distribution. So no discernible patterns. I mean, what is clear is that everywhere Kepler was looking, it found planets. So I think this has given us, I think, the right to claim that if you gaze up at the night sky and look upon a star in the sky, you can probably safely assume that there are likely to be planets around that star. Next, we have planetary exploration. What does solar system exploration teach us about the diversity of habitable environments, their evolution through time and life, and might human destiny include solar system colonization? So the researchers at the SETI Institute and elsewhere focused on planetary exploration are really all about looking at our own solar system as a laboratory for understanding life in the universe, and indeed whether life in our own life may exist even in our own solar system, let alone far beyond. And there's lots of interesting candidates, not the least of which includes Mars, but may also include moons of other planets like Enceladus of Saturn or Europa of Jupiter. So SETI Institute has been involved in many NASA missions, involved in the exploration of our own solar system. That includes the Curiosity rover, where a team of SETI researchers, together with their colleagues at NASA Ames, developed the X-ray diffraction system that's on the rover. We were involved very heavily in the science team of the New Horizons space probe that famously flew by Pluto last year in July. One of our scientists, Mark Showalter, was responsible for navigating the craft by using Hubble data. So on the approach to Pluto, we could be fairly certain that it wouldn't run into anything, which would be rather catastrophic. And as a result of his work using Hubble to study and chart the path of the craft, he discovered 2 of the newest moons of Pluto. So we've had a lot of involvement on the science team of New Horizons and also of the Cassini space probe, which has been used to unravel Saturn's rings, unlocking orbital anomalies of the moon Enceladus. So a SETI researcher has used Cassini data to determine looking at the anomalies of rather strange wobbling of Enceladus as it orbits Saturn, and finally was able to get a model that seems to map identically to the orbital characteristics of that moon, and that model suggests a solid core, a liquid water outer surface, and an icy surface with no physical connection between the icy outer surface and the core. As I told him, what he had discovered was the M&M peanut of the solar system at the time. But SETI scientists have also used Cassini data to determine that the rings of Saturn, which have always been both a beauty, object of beauty in the night sky, but also a thing of mystery, may be quite young. They may only go back as far as the age of the dinosaurs. So very interesting research coming out of Cassini. So that's the kind of work that our researchers do in planetary exploration. And then we have climate and geoscience. What are the physical and chemical processes driving planetary climates? How do life and the environment influence each other? How might climate change impact human life? So for this, we like to go far afield. In particular, we like to go to the Antarctic. Our researcher, Dale Anderson, and his colleagues do work in this area called Lake Untersee. Lake Untersee is a large freshwater lake at about 1,800 feet altitude in the Antarctic, and it is a fascinating place for extreme biology studies and also studying the interplay between biology and environment. This is a case where getting there is truly half the fun. So it's quite a journey just to get from his base of operations on the East Coast down to the South Pole. And once you get there by plane and get to your first base, there's a minor 6 to 8 hour journey on snowmobiles to get out to Lake Untersee from the base camp. And then it's a rather trivial matter of drilling a hole through 3.5 meters of ice, widening that hole with a heating element, and then jumping in. What could be easier? So this is Dale suiting up and getting ready to take a dive into the lake. And you definitely require some warm gear if you're going to go swimming around under the ice. But the rewards are quite spectacular. This is a picture of Dale under the ice. And you can see it's really a lot like diving in the tropics. It looks exactly like Hawaii and other places here. But the rewards are indeed pretty spectacular. These are mounds of cyanobacteria that are basically calcium-secreting organisms that thrive in this lake. And other interesting species have been found in this lake where there's no natural photosynthesis taking place and extremely cold conditions right around the freezing point of water, and yet life exists. So this is another interesting place where in the study of life beyond Earth, or Are We Alone, we see information showing us that a variable of the Drake equation is moving to the right. extreme biology tells us that the conditions under which life can exist, if you think about the envelope of conditions involving temperature, acidity, pressure, water, or the absence of water, oxygen, etc., are much larger than we originally thought, than was thought even 20 years ago. So you combine that picture of an expanded presence of life that is extremely robust with the fact that planets are now known, thanks to Kepler and GPI and others, to be everywhere, and it suggests that the probability is going up, that we are certainly not alone. Next, we have the astrobiology work. Our astrobiologists ask questions like, how does life begin and evolve? Does life exist elsewhere in the universe? What can terrestrial research teach us about biosignatures beyond Earth? What technologies can we develop to detect them? So here we make a different journey. This is research that takes place more or less every year and is led by our own Carl Sagan Center director, Natalie Cabral. And her work takes her to the Atacama Desert, into this region bordering Chile and Bolivia, where there's high, dry desert and volcanoes rising up over 20,000 feet, and in some cases lakes suspended in these volcanic peaks far above normal lines of conventional life, tree line, etc., and in places where there are extreme conditions of environment, not the least of which is extremely high levels of UV radiation. And yet here again, we find that life is quite robust. This is the area in which you work. So you can see very dry, very arid, very devoid of life on the surface, so it would seem. But of course, we know that life is abundant there, just like it is, for example, in our own deserts in North America. But this is the base camp, which they forgot to put a roof on, but I think there's a reason for that. And the team climbs up these peaks and investigates volcanoes at the top of these peaks. Here's an example of one of these small lakes with a red algae bloom that has adapted to extremely high levels of UV radiation, and maybe can teach us a lot of things, not only about the robustness of life, but the adaptability of life to extreme conditions, and indeed may even teach us things indirectly that are of use to, for example, oncologists in the study of cancer. How are organisms modifying their DNA and RNA to adapt to these kinds of environments? So quite spectacular in this rather rugged beauty of the Atacama Desert. Here's some more scenes, and not only are you rewarded with this beautiful scenery if you're doing research down there, but you have these very comfortable, flat, plush campsites to relax in between your excursions. But here again, you're rewarded with some interesting finds. Here is an example of salt flats around these lakes and around the Atacama region. They look like they're devoid of life. It looks like there's nothing there. But you break open the surface, and what you find is bacteriological life forms existing in abundance, hidden underneath the salt. And again, what are the processes, what are the life processes that are supporting this kind of life and living organism? And here you have an orange algae bloom, and you can see this particular algae has a flagella, so this is a very interesting life form that has adapted to levels of UV radiation that, in the presence of certain UV storms that have been detected by Natalie and her colleagues, are at radiation levels that would be fatal to humans. So adaptability of life is one of the key areas of extreme biology and the work of our scientists in the astrobiology sector. And then finally we have SETI, the search for extraterrestrial intelligence. Are we alone in the universe? Are there advanced civilizations we can detect? And what would be the social impact if we do? How can we augment the odds of making contact? Of course, one of the ways we augment the odds are by using now new techniques, including optical techniques. We're also working on, and you'll be reading more about this in the coming weeks, we're working on broadening our thought processes around what is really an anthropocentric view of looking for life in the universe, because we are in many ways looking for ourselves. We talk about the idea that we're sort of looking in a mirror when we're relying on technologies of conventional SETI work to look for life beyond Earth. There are very logical reasons for doing this, but what if what we're looking for is not another version of ourselves, but something entirely different? So you'll be hearing more from the Institute about our expansion of thinking around the SETI question. But we have the world's only devoted instrument to SETI, purpose-built for this for the purpose of looking for radio signals. It's located in Hat Creek, just to the east of Redding, California. It sits between the Lassen Volcano National Park to the south and Mount Shasta to the north. It's about 4,000 feet altitude. It's in a radio quiet zone. Radio quiet by virtue of the fact that nobody lives there, not necessarily by design. But it's a stunning location. It is open to the public. It's kind of fun to go and see and visit it. So if you happen to have the opportunity and you're traveling in that part of the country, you want to see the beautiful Lassen Volcano National Park, stop and visit Hat Creek. There's a visitor center. There's tours that you can do around the site, and you can learn about the work that is done there. But using feeds that are in the nose of the dishes that are sensitive to electromagnetic propagation in the 1 to 15 gigahertz range, we scan across that frequency range, and we listen for narrowband frequencies that would belie the presence of alien technology. And we're listening 365 days a year. Other efforts which have to rent time on telescopes, whether that be something like Green Bank or Arecibo or Parkes, et cetera, can only do so in chunks of time. And since, as I mentioned, the problem we have is not just a spatial problem, but a temporal problem, the ability to actually listen every single day, 365 days a year, is very, very important. And also to do so with an instrument that was purpose-built for this, and among other things, has the capability, more than other instruments, to differentiate between real signals and what might be false or human-originated signals. Here are some specifications. There won't be a quiz, but you can learn more about the telescope. And again, I encourage you to visit the site if you happen to be in that part of the world. We have now a new website devoted specifically to the SETI work we do with the Allen Telescope Array. It's at setiquest.info. And if you go there, you can see what we're observing. You can look at data from when we've done different observing. Right now, we're doing some interesting observations on red dwarfs. We most recently, we looked at Tabby Star, and I think very recently, we went back and revisited the so-called WOW signal that happened in, what was it, 77, yeah, back at Ohio State. So we've revisited that part of the sky to see if there's anything interesting to be found. So the nice thing about when you own your own telescope, you can do whatever you want with it, whenever you want with it. So if you want to find out more about what we're doing, what we're looking at, what we've discovered, there's also a star field map on that site where you can click and drag the star field and look at data from different observations that we've had. So very interesting. And as I mentioned earlier, we're also now developing an optical SETI program. We have a proposal in for the deployment of a worldwide optical SETI system, which would be based at 6 observatories, 3 in the southern hemisphere, 3 in the northern hemisphere, and give us all sky, all the time observation capabilities for looking for laser pulses. So that's an overview of the Carl Sagan Center, and now we'll take a visit to the Center for Education. Edna DeVore is our director, and as Edna says, our education programs share the excitement of exploration, the joy of discovery, and the wonders of the universe with children, educators, and adults. And we indeed cover that full spectrum in the work we do. We're strong supporters of STEM education, where we leverage our broad science and engage our researchers with the public. So there's some wonderful examples of the work that Edna and her colleagues do. One of them that you've probably heard talks here about before includes the Sophia plane. The Sophia plane is a modified 747 operated by NASA and the German Space Agency. It incorporates a 2.5-meter infrared telescope in the back end of the plane that floats in isolation to the plane's vibrations. What we do is we take teachers from all over the United States and give them an experience of not only going and viewing and looking at the plane and learning about the work that they do, they get to go on flights. So the teachers in what we call the Airborne Astronomy Ambassadors Program really get to experience science in the field and working and observing scientists doing their work in this real live classroom. And the whole point is they take the wonder of that experience and the passion of being able to experience that kind of research and bring that back to their classrooms and their school districts. We've been running this program for many, many years, including on the predecessor airplane to the current 747 SOFIA program, and we hope to be continuing to do that. And indeed, we're looking at ways of expanding that program that would give us reach to even a larger number of teachers. There's only so many people you can put on a plane for a given flight, but there's lots of other ways to experience the SOFIA science that is done. A program that is one of my favorites and for which Edna will forever be my hero is something called Reaching for the Stars. This is a NASA science-funded program for the Girl Scouts, and it was conceived of by Edna and her colleagues. And this is a program of informal education and merit badge development for Girl Scouts. This will be impacting girls from ages 5 to 18. It's conceived by the SETI Institute. It was developed in conjunction with NASA and the Girl Scouts of America, and the University of Arizona, the Astronomical Society of the Pacific, and Ares Scientific. And this kind of program, over its 5-year run, will certainly impact hundreds of thousands of young girls. And this is all about bringing STEM and the excitement of science education to young girls. So we're very excited about a program where, again, derived from a relatively modest institute of the size of the SETI Institute, to develop a program that can have such a huge, huge impact. We're very, very proud about that. NASA is also very, very happy about it. And many of Edna's colleagues in our science community complain because when you write a grant proposal to NASA, they come back whether you were successful or not, and they'll tell you what your strengths and weaknesses were and so forth. And in Edna's proposal, there were no weaknesses. And even our most successful scientists writing and submitting a proposal, they'll get something back which says, oh, this is a minor weakness, here's the money anyway. In Edna's case, there was not a single flaw they could find. So this is a wonderful, wonderful program we're very excited about. We also have, as I mentioned at the beginning of the talk, our summer internship program. This is funded by the National Science Foundation. It's called the REU program, Research Experience for Undergraduates. And in this case, we're partnered with the National Science Foundation. We bring about a dozen students in a very competitive process to the Institute. They spend 10 weeks with our scientists. And in fact, they are paired with an individual researcher on an individual project. When they apply, they're applying for a specific mentor. So it's wonderful that we have, in fact, more mentors than we do students in terms of the budget of the program. We have a lot of scientists very enthusiastic about their role in training and teaching the next generation of scientists. They devote their time, but the students work extremely hard. They are doing weekly reporting, and they culminate with an event which we will do right here at the colloquium, where they will talk about the work that they did over the summer. So this is a wonderful program that again runs 10 weeks and becomes really, I think, a game changer for the students who get in. And by the way, I mentioned competitive nature. So there were 250 applicants for about 11 positions this year. So we've got some very, very bright, capable young students participating. The Center for Outreach is where this is the place where we have different vehicles to communicate the work we do with the public at large. So we have our weekly public colloquium, which you're sitting in, which is always done here at Microsoft, always on Tuesdays at noon. And we have a content-rich website. We have a media presence on the social media. We have an hour-long nationally broadcast radio program called Big Picture Science. And we bridge the arts with our science through an artist in residence program at the Institute. So Dr. Seth Shostak, our senior astronomer, is in charge of our outreach activities, and he notes outreach at the SETI Institute is more than just a nice thing to do, it's an essential part of our mission. Not only does it make our research accessible and understandable, it highlights the relevance of our work to the public, and it promotes an interest in science among young people, which is, again, from our perspective, a very key part of our mission. So the weekly radio broadcast, again, was called Big Picture Science, and for those of you who are regular listeners, you know this, but Big Picture Science is more than just the science of the SETI Institute. In Big Picture Science, we really explore a wide range of scientific questions and problems and interesting topics. And what I like about big picture science is, they're never far away from what is the so what. What is interesting, what is impactful, what is meaningful about the story we're talking about today. Again, it's carried by over 100 NPR stations nationwide, and you can listen to it as a broadcast or a podcast or radio on demand. You can get it from our website. Interestingly, the City of New York, the Mayor's Office of Education, operates a radio station of their own on the FM band, and they recently just selected Big Picture Science to be included in that. So we're very proud of this program and its huge role in the outreach of the Institute. And if you haven't listened, I urge you to listen. It's really, really brilliant. The SETI Talks, as what we call the weekly colloquium that we're doing here. And as talked about at the very beginning, it's normally a very deep dive into the world of science that we do: astrobiology, aerospace, aeronautics, SETI research. We have probably by now over 360 lectures. They're all recorded on and made available on our YouTube channel, and they're archived and accessible through our own website. So there's several PhDs worth of knowledge and education and information on this long history of the SETI Talk series, which again is a very important part of our mission and something we're proud of and something we're very thankful to Leonard for supporting us for this year. Some of the recent talks we've had include talks about sand seas in the solar system, work on wind and wind erosion on Mars by Laurie from the Institute, orbital dynamics suggesting a recent formation of Saturn's moons, which Matya has done, and I alluded to that work earlier when talking about Cassini. SETI in the computational universe, which was given by Stephen Wolfram of Wolfram Research Institute. So these talks, as those of you who are familiar know, involve researchers from academia and from other institutes around the world, as well as scientists from the SETI Institute. Our website, of course, is something that is, again, a constantly updated source of information about the science we do, the education we do, and the work we do. So I encourage you to visit it often because there's always interesting stories. Some stories that we derive here are not stories that will end up necessarily in papers. They tend to be fairly up to the minute, but we do also share news about peer-reviewed papers and publications and other events that we're participating in. So there's always something fun and new to learn by visiting the website. And again, this is where we really, the primary vehicle through which we share our work with the world. Our Artists in Residence program is a program that really is about the exchange of ideas between artists and scientists, the mutual, I could say, motivation, stimulation, and inspiration that each other has. And the artists in our program spend time with our scientists, understand their work, and try to interpret this in ways that are meaningful to them. And often what our scientists find are, gee, what I'm seeing here in the way you've interpreted my work gives me a new way to even think about it. So the Artists in Residence program is a relatively new but emerging and important vehicle of sharing our science with the world. Charles Lindsay is the program director, and it was really a chance meeting between Charlie and Jill Tarter that established the Artist in Residence program in the first place. So we're very excited about that program. Charlie notes that we're now an international leader in this movement to integrate the arts and the sciences. Our artists bring fresh eyes to help navigate difficult concepts and act as a bridge to broaden the awareness of the science carried out at the SETI Institute. I was recently with Jill and Charlie and others in Massachusetts at a wonderful museum there called the Museum of Contemporary Art. It's out in the western part of the state, and this is they're currently doing an exhibit called Explode Every Day, an inquiry into the phenomena of wonder. And it's a program of an exhibition of the art of over 23 artists from around the world, 4 of whom are artists in residence at the SETI Institute. So we're proud to have this representation at this wonderful museum. This is one of our artists' work is a timeline of history of the universe from the Big Bang all the way around to the present. And this timeline occupies 3 walls in a major gallery. So it was a wonderful, wonderful work. The galleries themselves are big and airy. The museum is a converted textile mill, so a fascinating place in its own right, and wonderfully huge exhibition space. We'll also be at the Los Gatos New Museum in November of this year. They will be doing a dedicated display of the work of the artists from the SETI Institute. So we're very happy to have the artists as part of who we are, part of what we give back at the SETI Institute. So with that, if you're interested and want to follow us and want to keep track of what we do, you can be a friend of ours on Facebook or follow us on Twitter or Google Plus or link with us on LinkedIn. Lots of ways to stay up to date. We do use these social media platforms. Press releases and other news and information coming from the Institute is leveraged off of these platforms. We're making several posts a day, so you can stay up with the work we do through those platforms. And with that, and that story of the SETI Institute, I thank you very much for your attention, and I'm very happy to entertain any questions you might have. Okay.
1, 2, 1, 2. We use the microphone because we record the questions. Does anybody have a question they'd like to ask? I'll bring you the mic. All right, I get to run up the center aisle.
I guess I'd like your opinion about an issue. Astrophysics has a lot of challenging questions that are pretty much answered now. We know a lot about the origin of the universe. We know its age to 1%. Cosmological parameters are well understood. Gravitational waves and so on. On the other hand, in biology, I think the two fundamental problems: how did life originate, and is there intelligent life elsewhere in the universe? One could argue that we're maybe close to answering those, or maybe we're not so close. What is your opinion about that kind of difference between the physical sciences and the biological sciences?
Well, I think one of the things that's interesting, of course, is the interrelationship between the physical sciences and the biological sciences. I mean, the impact of biology on environment, the impact of environment on biology are interesting questions. And when you talk about the impact of biology on environment, you're talking about how does biology influence, for example, the chemistry of the atmosphere, and vice versa. I think, we speculated on this question of how close are we to finding life elsewhere. We did a panel session. Natalie and Seth, Fergal Mullally and Mark Showalter, our New Horizons scientists, were all part of that. And we were asking that question, are we close? When do we think we will find evidence of life beyond Earth? And my own take, we had, I think, answers that ranged from sort of 10 years to 50 years, and then Mark Showalter, wanting to be provocative, said maybe never. But my own feeling is, within the next 30 years and maybe sooner, we will find evidence of life beyond Earth. I think in our solar system, not technological life, but biology that we can detect either directly or indirectly and definitively. My feeling is that's not very far away, hopefully even within my lifetime. The question, and I think it's fascinating, and we don't know the answer. We talked about this transition from, how do we go from chemistry to biology? We don't understand that transition yet, although I think we're getting close and closer. But clearly, to me, that bridge is where these two issues of the physical and the biological sciences come together, and we don't know what that bridge looks like yet. But I think we're not far from understanding that. And again, within sort of this 20-year time frame, we should be able to do it. And this is what I think is so fascinating about the time we're in now, because now, more than any other time in our history, we have the tools available and the resources available to answer a lot of these questions, many of which I think will be answered in the coming decades.
Hi, Bill. Great talk. Thanks.
Thanks, Cliff.
In the previous talk that you alluded to just now, other than the notion that if we were to find ET, you guys would get a lot more funding.
That's true.
As the director, what would you say you, through the use of the Allen Telescope Array or through finding things, swimming around in the oceans of Europe or whatever, as time goes on, solved the Drake equation and actually got a number, then what would you see other than, trying to figure out how to spend your millions of influx? What would you see as the role of the SETI Institute changing from, right now, it's a questing thing. I mean, calling it SETI Quest for one of your websites is really appropriate, but it's a fundamental shift if the quest is in some way over, right?
Sure.
What's the
Yeah.
plan?
Yeah. I mean, I think that in terms of answering that question definitively, is there life elsewhere? You could say that question as part of our quest would be answered, but then how did it happen? And under what conditions did it happen, and where might those conditions be replicated so that we could find it elsewhere? I think that would be kind of the next role, would be taking those additional steps of understanding. So it would be a great moment to be at the helm here and say, we've got definitive proof. It wouldn't be as great as a signal. That would really be, this is definitely where I want to be when that happens. But seriously, I think that the role would transition to more of, okay, now we've found what we all believed, I think most of us believed, was there all along. That's the evidence of life beyond Earth. What does it mean? And again, what else do we have to learn from that? I think the learning, if you will, the number of questions would probably grow exponentially with that discovery. So rather than saying, we've begun to now confine our mission into something narrower, we'd probably be broadening that mission into something wider, my take.
Excellent talk, thank you. Can you comment on the possibility of detecting life outside the solar system that hasn't advanced to the point where it sends radio waves out into space?
Yeah, that's a great question. This is a question that relates to a technology that is evolving and developing, something we call biosignature detection. Do we have the ability to remotely detect the presence of biology far, far away, for example, on exoplanets? And there's lots of different efforts underway to define what those biosignatures might be. Are there biosignatures that we could detect based on the chemistry of an atmosphere? Are there other signatures that could be detected through spectroscopic analysis, et cetera? One of the things I mentioned that the SETI Institute is at a point now where we're trying to develop and derive and plan our own missions. One of the missions that the Carl Sagan Center, under Natalie's leadership, is looking at is trying to develop CubeSat technology where, for example, we might launch a CubeSat, point it to Earth, take the resolution way, way down, and begin to say, okay, use the Earth basically as a model and say, can we develop definitive biosignature techniques using such a method that we could then deploy by turning an instrument around, aiming it at exoplanets, and seeing what we can learn. But I believe as well that in the coming decades, that capability of definitive biosignature detection of remote objects will be possible.
Thank you for a wonderful overview. My question is from the perspective of an educator. Movies have long been enamored of space and space exploration as their topic. And I was wondering, is there any theme or specific movie that you've seen that has furthered the mission of SETI? And is there anything that Hollywood has done that your reaction was, gosh, I wish they'd stop doing that?
Well, I mean, to be honest, I think most everybody, takes Hollywood for what it is, which is Hollywood and its entertainment. So I don't know that I'd go so far as to say, they've done things that I think are damaging. Potentially, with the possible exception that certainly Hollywood has had a lot of movies, starting with War of the Worlds, which is still a wonderful film, and Independence Day, about bad guys coming to do harm. That may not be the best thing for the work we do. That has probably been among the things that have influenced those individuals who are against messaging, the so-called METI. And I've asked the question internally to our scientists on a scientific basis, on the scientific merits, whether they think the concerns of people like Stephen Hawking, who is against this, whether they agree with that. And in most cases, our feeling is no, that there's not really sound scientific basis for that concern. So that might be one area that I think has created some perhaps unwelcome noise in what should be a more scientifically pursued question. But we have one of our researchers, Pascal Lee, has a documentary film called Mission to Mars, which documents a 2-year effort to bring a crawler-like rover up to Devon Island and the Houghton Crater above the Arctic Circle. And this is another Mars analog site where they develop even technologies of how you do rover missions. If we have, for example, scientists on Mars, what are the logistics behind bringing them into a craft that then goes out and explores, and how much science do they do? So they do all that kind of work there. That film just premiered in Los Angeles a few weeks ago. It's a documentary film that we hope and expect will be more widely distributed. So that's kind of a serious science documentary. And there are, numerous people who have come to us at various times talking about, possible television series or things like that to kind of do some what they call smart television and do some educational things exploring these research areas of the Institute. So we'd love to see, programming like that come along. But, Hollywood, if nothing else, films like Star Wars and TV series, quite interesting and provocative like Star Trek, have, if nothing else, helped capture the imagination and reminded us that, there's more to life than just what goes on in the streets of Chicago or San Francisco, and, there's a lot of wonder out there and up there. So I think in general it's positive. Any other questions?
Excellent talk, thank you. My question is about the 6 observatories you plan to set up around the world to look in optical wavelengths for laser pulses.
Yes.
My understanding is we've barely started to resolve exoplanets around stars. So how do you plan to look at laser pulses that are only coming from a portion of the exoplanets?
Sure. Well, a bit like the radio SETI, one thing that's important to note is that in radio SETI, or an optical SETI, as in radio SETI, we're not looking to derive an understanding of a message or to decode. It's really just to detect the presence. So in the radio SETI work we do, it's really about if we see a narrow band, what would amount to a carrier frequency coming from deep space and verified as not being local in its origins, we could say, okay, there's somebody out there that's communicating. We don't have necessarily the means to understand if there's a message in there, what kind of protocols are in that method, what kind of modulation has been used to embed or decode, or rather encode a message into a carrier. So it's really not about trying to understand a message coming in, it's just, is there something there? With the laser technology, it'd be the same thing. And we have the technology with lasers right here on our own planet right now to beam a laser into space that would shine several orders of magnitude brighter than our own sun for brief periods of time. We haven't coupled the mirror to the laser to do that, but we theoretically can do that with laser technology we have right now. So, but this, from our perspective, this would really just be about, oh, there was a flash. This came from deep space, or there's a pulse. It's a narrow band. We use a grating to basically spectroscopically separate light signals, and we can tell it's a short pulse, specific wavelength, and it must be something interesting, but we don't know what.
Let's thank Bill for a great talk today.
Thank you.
And to keep up a very long tradition here at these talks, I'd like to present Bill Diamond, our CEO, with a SETI Institute mug. Thanks again.
This is it's the only reason I gave the talk, actually, was to get one of these mugs, as I've said many times, highly coveted.
Yes.
It'll be on sale at eBay tomorrow for $100,000. So.
Yeah, there you go.
Thank you very much for your
Thank
attention.
you.